Lesson for EE2165, and in this lesson we will particularly discuss Nodal and Mesh Analysis. So before we proceed, let me just rehash that in the previous lesson we have explored the parts of a circuit diagram. We have branch, nodes, and loops of a circuit. We also discussed about um, circuit analysis by way of Kirchhoff's voltage and current laws to solve for whatever that is missing in a circuit diagram. So this new lesson that we have now is just a continuation of the KCL and the KVL concepts, and we are gonna apply them for this four-part lesson. So the first part would be nodal analysis. That's one. Second would be about still nodal analysis but with voltage sources. So our approach to the problem solving process would be quite different, but not very big difference. The third one would be mesh analysis, and the fourth one would be the mesh analysis with current sources. So once again, this is a four-part lesson. In this particular way of solving a circuit, you will still need the concepts of Kirchhoff's voltage and current laws. So let me just remind you there that this is just a continuation. This is not an entirely new lesson. So to start with, we have nodal analysis. Nodal analysis is also known as node voltage method. So nodal analysis, in this type of analysis we use node voltages. So the term node voltages is quite new for us since we go previously we went into straightforward problem solving process wherein we just tackle what is given in the circuit diagram. So in this type of analysis we are determining uh, the reference and non-reference nodes among others. So this isn't exactly an easy process, an easy approach to solving a circuit diagram, because once again we are continuing at the concept of Kirchhoff's current law, or KCL, and one tricky part about KCL, as what I've mentioned in the previous lesson, is the assignment of branch currents. So looking at this diagram, we have a circuit with predetermined branch currents. So that will help us in our analysis later on. So nodal analysis has three main steps. Step 1 is to select a reference node and assign voltages to non-reference nodes with respect to the reference node. So that's a lot of reference nodes going on. So the reference node in this example is the ground node, where the voltage is equal to 0. It is always the ground node that becomes the reference node because the voltage is 0, so anything that goes above that would be the voltage across the branches. So the ground node is usually represented by 3 lines at the bottom, and in other sort of electrical diagrams you would still see the same. Ground will always be represented by 3 lines at the bottom. So yep, that's it. That's our first step. So in this diagram particularly, we have 2 non-reference nodes and we label them as V1 and V2. So the voltage at node 1 is represented by V1, and the same is true for V2 at node 2. So we have it already in the diagram. So the second step would be to apply KCL to the non-reference nodes, or again at these two nodes 1 and 2. So again, just to remind everyone that KCL is an equation in terms of currents entering and exiting each node. So we have here at node 1, we have um, the current entering node 1 would be I1, represented by capital letter I. And the currents exiting node 1 would be these three currents I2, the capital letter I for I2, or simply put, the current source. And we also have two other exiting currents, small letters I1 and I2 in this particular diagram. So it doesn't end there. Once we got our KCL equation in terms of currents, we need to express these currents to its to a voltage over resistance form. Just to recall, this is simply put the Ohm's law. So Ohm's law expresses as I, or current, is equal to voltage over resistance. So in each voltage that we have in our KCL equations, we have to substitute it with the value, the hypothetical value V over the given resistance R. So however, in a passive sign convention, current flows from a higher potential to a lower potential in a resistor. So we have the flow of current is from a higher voltage down to a lower voltage. So to express that, we have higher voltage minus lower voltage. Going back to this diagram, since I2, this small letter I, the branch current in the resistor R2, passes from left to right, it is assumed that V2 is larger than V1. So that's just what it means. And the third step would be to solve for the remaining simultaneous equations. Since we will come up with two equations for this particular diagram, we need to solve them simultaneously. So we have two equations for two unknowns. So that is a determinate equations we can solve for what is missing. So you can. So this will be a sample problem for nodal analysis. So as you can see in the diagram, it's not the best diagram that you've seen. Sorry for that. But aside from the usual circuit elements, I've also written the branch currents as well as the two node voltages, node 1 and node 2, with its corresponding voltages V1 and V2. So this is already step 1 that I've already accomplished in this diagram. So now let's go straight to step 2, wherein we will we will write a KCL equations for these two nodes. So we have KCL at node 1. We have the current entering node 1 would be 5 ampere. So let's write there 5A, and the currents leaving this node would be currents I2 and I3. There. So aside from just writing the KCL, what we are gonna do next is we will express the currents by its node voltage equivalent. So we have Ohm's law, wherein I, or current, is equal to voltage over resistance R. So we have the value for resistance. What we are having as our variable would be our node voltages. So 5 will remain as is. Then I2 will be expressed as V1 minus V2 over the value of resistance R, which is 4. So as I said previously, the the current will flow, the conventional current flow will be from the higher voltage to a lower voltage. So if we consider this diagram, it is assumed that voltage V1 is higher than voltage V2. So we have V1 minus V2. And the next part of this equation would be for I3, which is the branch current for resistance, for 2 ohm resistance. So we have V1 being the voltage at that branch minus 0 since it is connected to the ground over 2. So to simplify this equation, we need to look for its common multiple. So we will multiply both sides of the equation by 4, and we have 20 is equal to V1 minus V2 plus 4 divided by 2, that leaves us with 2 V1. To simplify further, 2V1 will add with this V1, so we have 3V1 minus V2 is equal to 20. So that will be our first equation. Now let's do KCL at node 2. The currents entering node 2 would be 10 amperes plus I2, and the currents leaving this node would be 5 and I1. So doing what we did, the KCL at node 1, we have to expand the currents according to its voltage resistance equivalent. We have 10 plus I2. We've already divided the equivalent for I2. We have V1 minus V2 over 4 equals 5 plus I1. We have I1 will be represented by V2 minus 0 all over 6. So what's gonna happen next is that we will multiply both sides of the equation by its common multiple, and in this case it would be 12. So multiply both sides of the equation by 12. We have 12 times 10, we have 120 plus 12 divided by 4, we have 3. So 3V1 minus V2 is equal to 5 times 12, that will be 60, plus 12 divided by 6, we have 2, so that's 2V2. So simplifying further, we need to distribute this. 3V1 minus 3V2. Moving this on the opposite side, we have minus 2V2 is equal to 60 minus 120. So combining V2, we have 3V1 minus 5V2 is equal to negative 60. And that becomes our equation 2. So what's gonna happen next is that I will just tweak this equation so that we will avoid of the negative signs. We have 3V1 plus 60 is equal to 5V2. While on this equation, we're just gonna isolate the value of V2. So V2 is equal to 3V1 minus 20. And we are gonna substitute the value of V2 here. So substitute. And this becomes 3V1 plus 60 is equal to 5V2, which is equal to 3V1 minus 20. So we have 5 times 3, 15V1 minus 20 times 5, we have 100. And copying other terms, we have 15V1 minus 3V1 is equal to 60 plus 100. 15 minus 3, we have 12. V1 is equal to 160. 160 divided by 12. We have V1 is equal to 13.33 volts. So we already solved the value for V1, and then we will gonna substitute it back to here. So substitute, we have V2 is equal to 13.33 minus 20. So we have approximately 40 minus 20, and now the value of V2 would be 20 volts. So we have solved the value for V2, and we already have our node voltages solved. That's it. The next lesson that we're gonna discuss will be still about nodal analysis, but this time with voltage sources. So what makes this approach unique is that our nodal analysis, as previously solved, wasn't really a uh, short length solution. It was a bit lengthy, but with voltage sources, the solution will be a little bit shorter. So as I've written here, the voltage sources will make the nodal analysis solution easier, and I'm gonna illustrate you that. But before going into the sample problem, we have two cases for nodal analysis with voltage sources. So the case 1, in the first case, if the voltage source is connected between a reference node, which is the ground, and a non-reference node, which is based on this illustration is represented by V1, the voltage at the non-reference node is equal to the voltage source. So simply put, V1 in this illustration, in this circuit diagram, V1 is equal to 10 volts. Simple as that. Now for the second case, if the voltage source is connected in between two nodes, take a look at these nodes here, V2 and V3. In between these two nodes, there is a voltage source. So these two nodes now form a supernode, as indicated in the circuit diagram. A supernode is a combined non-reference nodes and is treated as a single node with a single KCL equation. So instead of coming up with different KCL node equations for nodes V2 and V3, the presence of the voltage source makes it a supernode, and thus we will only create a single KCL equation for the supernode itself. So again, the supernode, the voltage difference to between node voltages V2 and V3 is 5. Since 5 volts, since the voltage source, the positive side, leans toward V2, it is assumed that the V2 minus V3 is equal to 5 volts, or in other words, the positive terminal of the voltage of source minus the negative terminal of the voltage source. And after this, we will go with the usual procedure of doing the nodal analysis. So to give you an example, where's the example? Okay, there. This is a similar diagram to what you've seen on the example. So this is a bit messy, but again, I've already identified the branch currents I1, I2, I3, and I4, as well as the nodes I1, I2, and I3. So we have both cases, case 1 and case 2, in this particular example. So we are gonna solve for node voltages V1, V2, and V3. So according to case 1, V1 is now equal to 35 volts. As simple as that. So we're just gonna square it. Then the next thing that we will do is we will treat nodes nodes 2 and 3 as a supernode. So just to highlight this particular area here, and that it meant supernode. So the next thing that we will do is to create a KCL equation at the supernode. KCL at supernode. There. So we have 4 currents entering and leaving the supernode. So the currents entering the supernode would be currents I1 and I4 plus I4. And the currents leaving the supernode would be currents I2 and I3. So the next thing that we're gonna do is we will expand this to its voltage over resistance equivalent. So the V over R equivalent at I1 would be V1, which is equal to 35 volts over 35 ohms, plus our I4. We have I4 is right on the top. We have the voltage for I4 would be V1, which is again equal to 35 minus V3, the voltage at node 3, over again 35 is equal to I2. We have the voltage at node 2. We have V2 over 35 plus I3, which is represented by V3 over 35. So this automatically becomes 1, and what we're gonna do next is we will just multiply it with their common multiple. In this case we have 35, a lot of 35s. We have 35 times 1, we have 35 plus 35 minus V3 is equal to, these are all gonna cancel out anyway. So we have V2 plus V3. So just moving around with the equation, we have V2 plus 2V3, and that's equal to 70. That would be our equation 1. So the next equation that we will come up is within the supernode itself. We have V2 minus V3 is equal to 35. That automatically becomes our equation 2. So now we have two equations and two unknowns. We can solve this, and I would like to solve this by elimination. So just to isolate, V2 is equal to 35 minus V3, and I'm gonna substitute this one to equation 1. We have 30, substitute, we have 35 minus V3 plus 2V3 is equal to 70. We have 2V3 minus V3, so that's V3 is equal to 70 minus 35, we have 35. So our V3 is 35 volts. Now we have solved for our V3. The next that we're gonna solve would just be V2. So once again, substituting this to the previous equation, we have V2 is equal to 35 minus V3, which is equal to 35, and V2 is equal to 0 volts. So that's a bit surprising. No volts registered at node V2. So there we have it, our 3 node voltages. The solution is quite short compared to not having any sort of voltage source. So that's your sample problem. Next lesson would be about mesh analysis. So far we have discussed nodal analysis and nodal analysis with voltage source. Now let's move on to mesh analysis. So mesh analysis is also known as loop analysis or the mesh current method. So in the previous lesson, we've determined loop as something that is represented here by I1 and I2 in this diagram. And this is another type of circuit analysis which is quite similar with nodal analysis, only with two caveats. So first one is that this type of circuit analysis uses mesh currents instead of node voltages against nodal analysis. And the second one, this particular approach to circuit analysis continues from Kirchhoff's voltage law or KVL. So in the nodal analysis, we have upgraded from KCL, Now for mesh analysis, we have upgraded from KVL. So those are the two main differences that they have for both nodal and mesh analysis. So the difference between a mesh and a loop is that a mesh is a loop that does not contain any other loop with it. So these are exclusive loops. So that's how we define mesh. So mesh analysis has three steps. So the first step would be to assign mesh currents in a circuit. So in this particular diagram, we have mesh currents I1 and I2. And for uniformity, assume that each mesh current flows clockwise. So for this particular course, let us stick to a uniform direction for a mesh current, which is clockwise. So there you have it, already placed there in the diagram. The second step would be to apply KVL to each of these meshes. So we have already discussed KVL from the previous lesson several weeks ago. So we're just gonna apply KVL to each of these loops or meshes. And the third one would be to solve for the mesh equation simultaneously, either by elimination technique or Cramer's rule. So I've written quite a few notes here in the material that I gave you. Please do care to read them. Now let's jump into this sample problem. So we have a simple circuit diagram, and obviously the branch currents have already been identified, but what we are interested to find is the mesh currents. So let's draw the mesh currents first. We have I1, so that's for mesh 1, and then we have mesh current I2 for mesh number 2. So there you have it. Our first step is to draw the mesh currents. Now the next thing that we're gonna do is to create a KVL equations for each of these meshes. So to start with, let's do the KVL at mesh 1. We have negative 35 because it touches the negative terminal first, so that's negative 35 plus I1 So this will be a sample problem for mesh analysis. So as you can see in the diagram, the branch currents have already been identified. We have values for resistances as well as voltages, and what we're gonna do next, first is to identify the mesh currents. So we have this one as our mesh number 1, and it is the mesh current will be represented by I1, small letter I, and for mesh 2 we have mesh currents I2. So there we have it. The next thing that we're gonna do is we will implement KVL for each of these meshes. So we have KVL at mesh 1. We will write negative 35 because it touches the negative terminal first, plus the voltage at the branch at the first at the branch 35 ohms. We have 35 I1 plus 35, another 35 wait, 35 I1 minus I2. So we have to take note that on the middle branch, uh, we have two mesh currents which are flowing at an opposing each other. So we have to write I1 minus I2 for the mesh 1 is equal to 0. So to simplify this equation further, we have negative 35 plus 35 I1 plus 35 I1 minus 35 I2 is equal to 0, or 70 I1 minus 35 I2 is equal to 35. So that's it. Then let's do the KVL at mesh 2. So we have 35 positive because it touches the positive terminal first, plus 35 for the middle branch. We have 35 ohms times I2 minus I1. So in reference, at mesh 2 we have I2, but the current at the middle branch opposes the mesh current 1. So we have I2 minus I1 plus 35 I2 is equal to 0. So expanding the equation, we have 35 plus 35 I2 minus 35 I1 plus 35 I2 is equal to 0. Then we have 70 I2 minus 35 I1 is equal to negative 35. So we have our first equation right here, and now our second equation has already been obtained. So dividing both sides by 35, we have 2I1 minus I2 is equal to 1. Then over here, dividing also by 35 because that's the common denominator, common multiple, we have 2I2 minus I1 is equal to negative 1. So let's isolate I1. So I1 is equal to 2I2 plus 1. So let's substitute it on the first equation. Wait. We have 2I2 plus 1 minus I2 is equal to 1. 4I2 plus 2 minus I2 is equal to 1. Simplifying further, we have 3I2 is equal to negative 1. So we have I2 is equal to negative 1/3 amperes. So we've already solved for I2. Now let's substitute this back to the second equation. Substitute. We have I1 is equal to 2 negative 1/3 plus 1. We have negative 2/3 plus 1. The value of our I1 is now negative, no, this is not negative, positive 1/3 amperes. So we have the value of our I1. So there we have it, our mesh analysis. Now that we've already discussed about mesh analysis, the next thing that we will discuss will be about mesh analysis with current sources. So if we have nodal analysis with voltage sources, we also have mesh analysis with current sources. And again, it will make the mesh analysis quite easier. So this has two cases. So for the first case, if the current source exists only on one mesh, like what you've seen in this diagram below, the mesh current is automatically equal to the algebraic equivalent of the current source. So we have here in this particular example, I2, mesh current I2, and this loop has a current source of 5 amperes. Since they are of opposing direction, we can write I2 as equal to negative 5 amperes. So that's for case 1. Now, the second case for mesh analysis with current sources is that if the current source exists between two meshes, like on the middle branch, a super mesh is formed. If we have a super node for nodal analysis, we also have super mesh for mesh analysis. A super mesh is a combined mesh that excludes the current source and any elements connected in series to it. So, the way that we treat super mesh is that we will treat the branch, the middle branch with the current source, as if it doesn't exist. So we have diagram letter A. This is the actual problem, but if we are gonna redraw the circuit, it becomes that the middle branch of the circuit is gone. So that will make our problem solving quite easier. So first things first, we will start off with the solution by simplifying the given problem, which is from diagram A to diagram B, on a supermesh perspective by excluding the current source and any elements connected in series to it. So the 2 ohm resistor will be gone as well. So at diagram B, proceed with 1 KVL mesh equation with 2 variables I1 and I2. So you will come up with a single KVL mesh equation, but with 2 variables, mesh current I1 and I2. So we will use mesh current 1 for the 6 ohm resistor, but we will use mesh current 2 for resistors 10 ohm and 4 ohms respectively. By inspection in the given diagram, we can easily create the equation for the current source in between two mesh currents. So the way that we create an equation, a current equation for the super mesh, is that we will only inspect the diagram and check the directions of the mesh currents. So from diagram A, it is evident that the 6 ampere is equal to I2 because it matches the direction of mesh current 2 minus the mesh current 1 because it opposes the flow of the current at mesh 1. Okay? So we have our equations, and now the equations can be solved simultaneously. So I will give you an example. So this will be a sample problem for mesh analysis with a current source. So the first thing that we will do is that we will redraw the circuit. So we have this voltage source, we have resistor, but exclude we will exclude the middle branch. So we will just proceed to drawing the rest of the circuit diagram while avoiding the middle branch. So we have our ground, 20, 6, 10, and 4. So we will redraw this, but we will also have to determine our mesh currents. So we have mesh currents I1 and we have mesh current I2. Now for our redrawn circuit, we will do the same. We have mesh current I1 and then we have here mesh current I2. So by the way, just to indicate, this area right here is our super mesh. So we will exclude that. So we can now write our KVL equation for the simplified diagram. So KVL at super mesh, we have negative 20 plus 6I1 plus 10I2 plus 4I2, and that is all equal to 0. So we can simplify it. 20 is equal to 6I1 plus 14I2. So this will be we can simplify this further by dividing both sides of the equation by 2. We have 10 is equal to 3I1 plus 7I2. So this will be our first equation. Now to relate the current source from the original diagram, we have 6 is equal to I2 minus I1. So that simply becomes our equation 2. Now we can solve for these two equations by substitution or any other algebraic method that you fancy. So we have I1 is equal to I2 minus 6 and we will substitute this to equation 1. We have 10 is equal to 3 I2 minus 6 plus 7I2. We have 3 I2 minus 3 times 6, so that's equal to 18 plus 7 I2. So 3 plus 7, that becomes 10 I2, and 18 plus 10, that becomes 28. Divide both sides by 10, and we have I2 is equal to 2.8 amperes. So we have now solved for our I2. What we're gonna do next is we will just substitute it back to equation 2. We have I1 is equal to 2.8 minus 6. So our I1 is equal to 6. 2.8 minus 6 is negative 3.2 amperes. So that's our current at mesh I1. So we have our two mesh currents already solved, and as you can see, it is pretty quite straightforward. The solution is a lot shorter than a regular mesh analysis method, so it does indeed make our work quite easier.